Good morning, everyone. So today we will continue with the module 2, that is representative elements, where we are discussing the various groups in periodic table. So in the previous classes, we had done the chemical properties associated with group 1 uh, elements. Today we are going to start with the chemical properties associated with group 2 elements. So the first property that we are going to study today is the reaction with water. So we have already seen the reaction with water for the group 1 element, and there we found that whenever that element reacts with water, it forms the corresponding hydroxide, as well as it also forms the corresponding hydroxide, as well as hydrogen gases evolve. In a similar fashion, what you'll find here is that your metal reacts with water to form the corresponding metal hydroxide, and the hydrogen gases evolve. If we talk about reactivity of these metals, we find that beryllium atoms is a little bit less reactive, so it requires steam for it to actually react to give the corresponding hydroxide. However, magnesium, it reacts very readily with hot water. It doesn't require steam. It can react with hot water to give you the corresponding magnesium hydroxide. However, the rest of the elements in group 2, that is calcium, strontium, and barium, they react just with cold water to give their corresponding hydroxide. So this is in terms of reactivity. Now, if we look at the electrode potential, so this is the electrode potential for your beryllium, magnesium, then you have calcium, strontium, and barium. Okay, so this is kind of the electrode potential for the various elements of the periodic table. Now, if you compare it with the group 1 elements, what do you see? There is a difference here. In group 1, the electrode potential for lithium was negative, highly negative, and that explained why this should be very reactive in terms of thermodynamics. However, if we look into the group 2 elements, we find that the trend is a very similar, very natural trend of basicity. That is, as we move down the group, the basicity increases, and therefore reactivity also increases in the similar manner as you go down the group. So here, electrode potential is falling in line with the reactivity pattern that is shown here. However, in the case of group 1, that was not the case. The reactivity trend followed from sodium onwards. But before sodium, that is lithium, it was comparatively uh, opposite. Okay, so that is the difference that you will find in the electrode potential of group 1 and the group 2 elements. So group 2 elements, they are pretty similar to their basicity trends and the reactivity patterns that these elements shows here. Now, here, if you look at the magnesium electrode potential, it is highly negative. Okay, so that means it should be enough reactive to react in cold water. Okay, but what you find here is that in spite of the favorable E naught that this magnesium metal have, it doesn't react readily. Now, why that is so is because magnesium, when it reacts with water, it forms the oxide covering over the metal. So because of that, what happens? It protects the magnesium element from further reacting with the water. So that is why its reactivity is pretty less, even though it has a very favorable E naught value. And this formation of magnesium oxide coating over the magnesium metal, which reduces its reactivity, is also found in the group 13 element, that is aluminum. Okay, aluminium also shows a similar trend in their reactivity pattern. Now, if let us look into the hydroxide, the various characteristic of the hydroxides formed by this particular group. So, the beryllium hydroxide that is formed here is amphoteric in nature. It is uh, um, neither acidic nor basic. It kind of react with both. So that is why they are amphoteric in nature. However, the rest of the oxides, hydroxide of the other elements in the group 2, they are all basic and basicity increases down the group as we have already seen in the group 1 case. However, if we compare the basicity of the hydroxides of the group 1 with that of the group 2, what we find is that the group 2 metal hydroxide are less basic in comparison to group 1 metal hydroxide. So, because of the lesser uh, basicity of the group 2 metal hydroxide, as we have seen previously, their oxo salts, that is carbonates, sulfates, nitrates, they are kind of unstable and they decompose on gentle heating to their corresponding oxides. So whenever your basicity is low, the oxo salts, that is carbonates, sulfates, nitrates, they are unstable. So a gentle heating can decompose them into their corresponding oxides. This particular reaction we have seen in the previous case when we talked about the basicity of the group 1 elements. Now, here again, this reaction you are pretty familiar with. This is the way in which we can detect the presence of carbon dioxide. So, this is nothing but your uh, lime water, right? So, let me write it down for you. So, this is nothing but your lime water. So lime water is something that is used for uh, carrying out your detection of carbon dioxide. So whenever you pass carbon dioxide to through a lime water, that is CaOH twice, what happens is that you get the precipitation of this calcium carbonate, and this that gives turbidity in this lime water. That is because of the precipitation of the calcium carbonate. So this, whenever you pass carbon dioxide through lime water and you get some turbidity, that indicates the presence of that gas is what the carbon dioxide. Now, if you continue to pass carbon dioxide through this solution, what happens? There is formation of calcium bicarbonate, which is soluble, and this white salt solubilizes completely because of the formation of calcium bicarbonate. These particular reactions you are pretty familiar with. Now, similar to lime water, there is another water that is called baryta water, that is BaOH twice. All the reactions are pretty similar. This also, when it have the carbon dioxide pass through this baryta water, that is barium hydroxide solution, they also form their corresponding barium carbonate, and you can detect the presence of carbon dioxide. But what happens here is that these baryta waters are highly sensitive. Okay, so even your breath, your inhalation, your exhalation is enough to make this turbid. So if you are doing the detection of carbon dioxide, if you use baryta water, it can give wrong indication because your breath itself can give the turbidity in the solution. So that is why we don't use baryta water for the detection of carbon dioxide, but rather lime water for the detection of the carbon dioxide. So that is all about these uh, reaction of these group elements the uh, with the water. So I hope you understood whatever we discussed in here. We will discuss in the live session further, and you can ask your doubts regarding this particular topic. Thank you very much for your attention.